In this next example, we're again going to try to use the test for divergence to determine whether a series diverges or if we get to do more work. And this example we're going to do looks very similar to the first example we did, except instead of having cosine, we now have a sine of n squared pi over n squared plus 5. As a spoiler, we're going to see that we're not going to be able to tell whether this series actually diverges or converges for that matter. This is going to be a case where we're going to get to do more work. But for right now, let's just practice test for divergence and see how we arrived at that conclusion. So the test for divergence, we again want to know what the terms far out in that sum look like. If those terms look like anything but 0, the series is automatically divergent. So we apply a limit to basically see what those terms really far out in the sum start to look like. So let's take a look at the limit here. We have the limit now as n goes to infinity of the sine of n squared pi over n squared plus 5. And just like the previous video, when we look at where the n dependence is, we only see n dependence inside of the argument of that sine function. There aren't any n's outside of the sine anywhere. So when we're thinking about doing this limit is really inside of the sine function, if you will, or we can really just think about this limit as affecting what's inside of the sine. And then whatever that limit comes out to be, we just take the sine of it at the end of the day to see what this limit overall equals. So let's take a look at what this limit is. Again, we have, well, the same thing as a previous problem, but if we look at the numerator, n squared pi, as n goes to infinity, this numerator looks like it's going to infinity. And similarly, this denominator also looks like it's heading towards infinity. So we have an infinity over infinity, indeterminate form, so we get to use L'Hopital's rule. So the sine comes along for the ride because what L'Hopital's really is just affecting is that indeterminate form for us. So we're going to take the derivative of the numerator and denominator separately and then reevaluate the limit. So the derivative of n squared pi is equal to 2n pi. The derivative of that denominator, n squared plus 5, is 2n. So we would reassess what this limit looks like now. Do we get another indeterminate form, in which case we do L'Hopital's again, or does this limit come out to be some number? And well, for us, we can see that we have 2n factors in both the numerator and denominator. So this limit just comes out to be equal to pi. I'll just write this additional step just to illustrate this. So we have the limit as n goes to infinity. Since the two n's canceled out, we really just have the limit as n goes to infinity of the number pi, but there aren't any n's attached to that pi anywhere. So the limit of any number just by itself as n goes to infinity, or any constant by itself as n goes to infinity, I should say, is just equal to that constant. So this limit is equal to sine of pi. And now, sine of pi is equal to 0. So what does this mean? Well, what this means is the terms really far out in that sum, they all start looking like 0. But it doesn't guarantee whether that series or that infinite sum converges or diverges. So because this limit is 0, all this says is this series passes the test for divergence, so we get to do more work. So this example, by applying the test for divergence, it didn't really buy us any new information. It just said, hey, the test for divergence doesn't work here. Pick another series test to do. So in other words, we get to do more work.